Good evening, everyone. Yes, we started our discussion on the measures of association. Today is Tuesday, last week. Yes, last week. So we want to conclude the measure of association. We talk about relative risk and odds ratio, the situation around using each of them. So to conclude the lecture, I just want to give more explanation on the interpretation of relative risk and odds ratio and the relationship between both of them, between relative risk and odds ratio, and also talk about how we can judge association by having the value of relative risk and odds ratio does not actually mean that there is an association between the two variables, between the exposure and the outcome, between the risk factor and the disease. It doesn't really mean. So how do we judge association? That I think we'll be looking at today. So let's first of all revise the interpretation. We said that we already said that odds ratio is a proxy to relative risk. And if any of them is 1, it means there's no even association between the exposure and the outcome because each of them is gotten by division. You divide the risk among the exposed by the risk among the non-exposed. So if the exposure actually caused the disease, the risk among the exposed should be far, far bigger since it's the numerator should be bigger in such a way that when you divide it by the smaller risk among the non-exposed, it should be greater than 1, not only greater than 1, the value will now give you the measure, the magnitude of that impact, the effect of that risk on the disease. So, for example, if it is 2, it is not as weighty as if it is 4 or if it is 10. So you see now the risk among the exposed is the numerator, the non-exposed is the denominator. So if you divide the 2 and I give you 1, it means that the risk is the same among the exposed and non-exposed. So there is no difference. Whatever you call exposure, it's not actually has nothing to do with the disease. That's what it means. If the relative risk or odds ratio is 1, it means there's no association. However, if the relative risk is less than 1 or odds ratio, it means that the value of the risk among the non-exposed, which is the denominator, is far, far bigger than the one among the exposed, which is the numerator. So in that situation, that shows that even the exposure is the one preventing the disease because the risk is smaller. That's why when you divide the smaller value by the bigger value, it gives you 0 point something. So it is when the risk is 1, the relative risk or odds ratio rather is 1. That is when you cannot say exposure is causing it. You cannot say exposure is protecting it. There's no even exposure has nothing. That factor has nothing at all, either protect or prevent the disease, either to cause the disease or prevent the disease. It has none once it is 1. But if it is greater than 1, it means that the exposure is actually contributing to the disease. If it is less than 1, it means that the exposure, what you call exposure, is actually preventing. So we also talk about how you interpret the confidence interval. We said that the confidence interval, how do we know? Because even without, if you do your analysis without p-value from the confidence interval, you can know whether it is significant or not. You can know whether it's significant or not. If the confidence interval, by the time you calculate your relative risk or odds ratio, and you also calculate the computer will give it to you when you analyze with the computer. And you now calculate the confidence interval of the relative risk or the odds ratio. If the confidence interval crosses 1, include 1 in its interval, that is the value, because you are going to give two values now, lower and middle. If the range of value, okay, for example, now, if it's 0 point something and the other one is 3 point something, you say the value in the population will be any value between these two values. If you say 0.67 and 4.3, between 0.67 and 4.3, 0.67 is less than 1. 4.3 is greater than 1. That means that it can be any value in between the two values, including 1, because the value 1, if you want to move from 0.67 to 4.3, you have to pass through 1 also. So that should have, what it means that 1 is one of the possible values in the population. And you already know that if it is 1, it means that there's no association at all. So that is why when the confidence interval include 1 in its confidence, we are talking of confidence interval odd ratio. We're not talking of confidence interval different between me. That one is a different ball game. So I think when we talk about mean t-test, we discuss that. That one it is when it crosses 0. So when anything has to do with difference between mean, when the confidence level crosses 0, you know that it's not significant. But this one, because you know that one is different between mean, you are removing, you are minusing one mean from the other. If two means that two things are the same, you minus 1 from it, give you 0. That's why the factor there is 0. When there's no difference, when you're talking of difference between mean, is 0. That is why the confidence level cross 0 is not significant. But here now, it's a matter of division because you are dividing risk and risk. One is numerator, one is denominator. So if both of them are the same, when you divide, give you 1. That is why 1 is the issue when it comes to whether it's significant or not. So when the confidence interval crosses 1, include 1 in its range, it's not significant. So for it to include 1, that's why that it starts from 0 point something and end anything after 1. So the confidence interval starts from 0 point something and end in 0 point something without crossing 1. This is significant. It's only that the factor you are talking about is protective. It's not actually causing disease, preventing it. But when the confidence interval starts from anything after 1 and end anything after 1, it's significant. It means that the factor you are talking about is actually causing the disease, is responsible or contribute to the causation of the disease or contribute to the disease. So that is why you can see now. So it doesn't really matter whether the odd ratio or relatively ab initio, whether it's less than 1 or equal to 1 or greater than 1. It doesn't really. Once the confidence interval does not, when the confidence interval include 1, it's not significant. So you see all those 4 possible, what I'm showing in this slide now, all those 4 possible ways you can perceive of it. Look at it when on this left side now, you see the confidence everything less than 1. So less than 1 means that anything, if the first one, both the lower and upper, they are below 1. That shows that it's significant, but it means that the factor is protective. But the second one, the lower one, of course, you know that the value of the relative will be in between the lower and upper. That's just it. That's the dark area in the line. So the horizontal line, that thicker area, that is the value of the relative risk or odd ratio. The lower end, the extreme end are the lower and the upper. So when both the lower and upper less than 1, of course, it means that the relative risk you are calculating is less than 1 ab initio. So it's significant. It means that the factor is protective. But the second one, yes, the relative risk is still less than 1. But the confidence interval ranges from less than 1 to 1 greater than 1. It has crossed 1. So it's not significant. That shows that what you see is just by chance. It's due to chance. The third one, yes, the relative risk is greater than 1. But the lower end of the confidence interval is less than 1, while the other one is greater than 1. So it has included 1 in this. It's not significant also. But the last one, of course, the relative is greater than 1. Both the lower and upper, they are greater than 1. It shows that it's significant. That shows that factor is responsible for the disease. I think it's very clear. Now, I was talking about relationship between odds ratio and relative risk. So odds ratio is a proxy. We say that in the situation where you cannot calculate relative risk, you calculate odds ratio. And let's prove it. Somehow mathematically from this table. Thank you. When the probability of an event, we already talked about probability, which is risk. I will compare with odds. That was last lecture. When the probability of an event happening is rare, or when the prevalence of a disease is rare, odds and probability are very close. In fact, I demonstrated that in one of the initial slides, that last lecture. When the prevalence of a disease is very, very small, the odds and probability, which is the risk or the prevalence. The prevalence is the probability of the risk. And the risk and the odds, they are very close. We know that if the risk is 0, odds will be 0. But as the risk is becoming greater and greater than 0, so the odds will be greater and greater than the probability of the risk in value. We already say when the risk is half, 50%, the odds is 1. That is 1. When the risk is greater than 50%, the odds, of course, becoming higher and higher than the risk. Until when the risk is certain, is 100%, the odds is infinity. That's gone to infinity. So you see, as the prevalence of the disease increases, the odds become greater and greater than the risk. But when the difference will be becoming wide and wider and wider. But when the risk is very low, even though the odds is greater than the risk, the value is closer and closer. So that is why, in a nutshell, whenever the prevalence of the disease is very low, whether it's a waste of money, even conducting cohort study, that you calculate the risk, because you need to calculate the risk and calculate the relative risk. So the odds ratio you calculate through case control or descriptive cross-sectional study will be close to what the risk relatively will have been. So odds ratio will be close to the value of relative risk if the disease is rare. Okay, look at you remember in the case, you say A is much smaller than, we remember the 2x2 table. You say risk among the exposed is A all over A plus B. The risk among the non-exposed is C all over C plus D. If the disease is rare, if you remember, A and the C, they are the one that have the disease. A is the one that have the disease among the exposed. C is the one that have the disease among the non-exposed. If the disease is rare, so the value, if you say A all over A plus B, the contribution to A plus B by that A is very small. So when we just say A all over A plus B, it's like saying A all over B. Because the contribution of that A to B in the denominator is very small. So it's like saying A all over A plus B is approximating A all over B. The same thing with C all over C plus D. the value of that C is so small that when you are saying C plus D, because D contribute much more. So we just remove that C and just say C all over D. And the odd ratio, if you remember, is AD all over BC. So when you now divide them now, AB all over divided by CD, if you do your change of you calculate, you will go to be AB times D all over C, which is AD all over BC. So in that situation now, relative risk and odd ratio become the same. So odd ratio approximate relative risk when the successes are rare. Successes here just mean that when you say successes, it just mean the prevalence. Odd ratio is sometimes referred to as approximate relative risk. Look at this table. Give some information, intuitive information concerning what we are saying. Let's say we have prevalent, we have population 2 and 1. We are comparing the maybe population 2 is the exposed, population 1 is the non-exposed. You know, the risk, that is the probability, sorry, the P2 is the probability risk in population 2. P1 is risk in population 1. So relative will be P2 all over P1. So let's look at the risk, the prevalence, when the prevalence of disease vary. Look at 0.1 in the first one is 0.1 in population 2, 0.01 in the other one, 0.3, 0.15, 0.5, 0.25, 0.7, 0.35. What you see is that the relative risk is constant. And sorry, the risk of the disease is constant. If you look at it now, it's not the risk of the disease. The risk of disease increases, you see the relative, it increases by the same proportion in both the exposed and not exposed. So it gives you the relative risk constant, 2, 2, 2, 2, 2. But look at the odd ratio. The odd ratio, because as the burden of the disease increases from 0.1 in population 2 to 0.3 to 0.5, you know the burden of the disease is increasing now from 10%, 30%, 50%, 70%. Whereas in the control population, 5%, 15%, 25%, 35%. It's increasing also. So as the burden of the disease increases, even the relative risk is still the same, but the odd ratio increases. And you will begin to see that the value of the odd ratio when the prevalence is lowest here is 2.11, whereas relative risk is 2. It's very close. When the body increases further, even the relative risk is 2, the odd ratio becomes 2.42. It's increasing, and the distance, the difference between the relative risk and odd ratio begin to widen, increase. So just to demonstrate that when the disease is rare, the value of relative risk and value of odd ratio approximate that of relative risk. Now, this one further strengthens the relationship between them. This explanation. Now, there's something. When events occur equally in both the exposed and the non-exposed, relative risk is equal to 1, odd ratio is equal to 1. You know that. The odd ratio is always further away from 1 than the relative risk. So when the relative risk is less than 1, the odd ratio is less than relative risk. When the relative risk is greater than 1, odd ratio is greater than relative. Don't know if you get it now. Relative risk and odd ratio are more similar when the baseline risk, reference risk of the probability of event is small. So if the risk is small, the relative and relative ratio, they are very close. But when the relative risk is less than 1, the odd ratio is less than relative risk. But when the relative risk is greater than 1, the odd ratio is greater than relative. Look at this graph. The graph plots odd ratio at the vertical axis and relative risk at the horizontal axis. So for different study, whatever. So different study, you see now different color. So when the risk is 10%, that is when the risk is 20%, down lemon yellow is when it is 20%. When it is 50%, 80%, 90%, for different value of the risk. Look at it. Now, let's choose a point. Let's say we choose a point. Let me look for a hand. Let's choose one point now, where relatively, which is horizontal, where this relative risk now is 0.5 here, which is less than, let's choose any of the graph. Let's choose this red one, that red one. So let's see, when the relative risk, which is the risk ratio, you know, relative risk is the risk ratio. So when the relative risk is 0.5, which is less than 1, let's trace the graph. We trace it to this place. Let's do horizontally to know the value of corresponding odd ratio. Can you see? The corresponding odd ratio is less than that 0.5. Whereas the relative risk is 0.5. The odd ratio, corresponding odd ratio is less than that 0.5. Because the relative risk of 0.5 is less than 1. Let's choose from the same red graph where the relative risk is higher than the odd ratio. Let's see, there's higher than, 1. From here now, look at this 2.5 position. Is greater than 1. Let's trace the thing up. Okay, it doesn't. Okay, we can trace it on. Let's choose the blue line, blue graph, because the red graph does not reach that way. Look at it. Look at this blue. Let's trace it back to the corresponding value of odd ratio. Can you see? At the relative risk of 2.5, which is greater than 1, the corresponding odd ratio is greater than that 2.5. It's like maybe 2.6 or whatever. Or more, even more than that, or 3. What am I saying? 2.6, maybe the other one is 5. Is something like maybe. You see? You can see the demonstration now. So when the relative risk is less than 1, the corresponding odd ratio is less than the value of the relative risk. But when the relative risk is greater than 1, the corresponding odd ratio is greater than that value of relative risk. The reason means that what is just follow the relationship between risk and odd also. You remember, the risk is narrow, the range of value is narrow, is from 0 to 1 or 0 to 100%. Risk is probability. Prevalence is probability. You cannot say prevalence is more than 100%. No. Greater than 100%, everybody has that thing. So it cannot be greater than 100%, which is 1. It cannot be less than 0. You cannot say minus. Nobody has it. That's the prevalence of 0. So risk is between 0 and 1 or 0 and 100, depending on which scale you are using. Are you using fraction, decimal, or using percentage? But the odd ratio, the corresponding odd, is ranging from 0 to infinity. can have big value, 900, 1,000, 1 million to infinity. Can you see? From 0 to infinity. It's the same thing for relative risk, even though that one is not from because it's not risk, it's comparing risk. So it's not from 0 to 1. It can be anywhere, it can be 50, it can be any value. But the range of value is still narrow. While the range of value of really corresponding odd ratio is wider. So odd ratio, we have, if you have a value, any value less than 1 in relatively, the corresponding odd ratio will be far less than that value. Once you have value greater than 1 in relatively, the corresponding odd ratio has value higher than that. So you can see odd ratio has wider range of value. So the range of value of relative is in between. While that of is like you're drawing a line like this. Let me this here. I'm trying to take back that. Okay. Yeah. It's like you are drawing something like this. This narrow margin, that is relative range of value of relative risk. But the wider margin, range of value of odd ratio. So let's say the relative risk from here to it cannot be less than maybe range of value, positive value between here and here. For the odd ratio is wider, it's from here and here. So the range of value of relative risk is captured within the range of value of odd ratio. That's just a summary what I'm saying. Let me clean the, what is the brush to clean? Okay. I don't know if there's any question before, because I'm going to the next one, judging association. So many a time, you know that it's more difficult to conduct study that will calculate relative risk. But the study you conduct to calculate relative risk has to be whether experimental design or core study. And both of them, you look forward. They are prospective in nature, in the side that you start and you finish somewhere in future. For example, now, core study is the most expensive study because it's not like it's more expensive than experimental design. Because experimental design, you design your experiment, you have your protocol within the time, even no matter how long you have, you have the time frame within which you want to finish it, collect your post intervention data, and do the analysis. Whereas the core study depends on the natural occurrence. But what you do that you see those factors, for example, smoking. This smoking is responsible for lung cancer. You now gather people that are smoking together, people that are smoking now. You try to recruit them. You also recruit some people. The people that are smoking now, you recruit, they call them cohort because it's at the same time they are smoking. They are cohort. While you also gather some people that are not smoking also. You try to follow up, you begin to see what will happen. You are not the one that asked them to be smoking. You didn't give them cigarette, but that's their lifestyle. You just study them at their natural state. Then the other people that are not smoking, you didn't help them not to smoke. That's their lifestyle. You now follow up. You know that type of thing. You have to wait for many years to begin. As you are following up, you are recording occurrence of lung cancer among both groups. It can happen among the people that are smoking. It can happen among the people that are not smoking. You have to follow up for many years. Sometimes, if the disease is a rare one, you may even follow up for 20, 30 years. You may not see one case. Can you see? At the end of the day, if you now see few cases, it may not even be enough for you to make any meaningful conclusion. That's why look at this Birmingham study they did in America for studying the risk of coronary heart disease. They spent 40 years. Can you imagine? 40 years. There have been some of the investigators say that will have even died. They did the course study for 40 years. They recruited people and followed up for 40 years before they did the analysis. See? And sometimes if it's a disease that is very rare, you can waste money for 40 years, nothing, you cannot get anything. So because of the knowledge that though if the disease is even rare, the value of odds ratio approximate that of relative risk. Because of that, okay, if the disease is even rare, why not just do case control? Any case of disease you find, you now use it to do your study. Because in case control, the person has already developed the disease. It's just for you to ask questions about past experience. If the person was exposed to the risk in the past, that's the logic. Same thing with the where you just question people. They have disease or they don't have it. The risk you ask for the disease and the risk at the same time. Whichever way, whether case control or cohort study, case control or cross-sectional descriptive study, whichever way, any of them, you'll be able to calculate the odds ratio. Whereas you cannot, if you are in that situation, you cannot calculate anything, but you cannot calculate it because the thing has occurred. So with the knowledge that when the disease is rare, odds ratio approximate relative risk. People do for any rare disease, they just do simpler study, less expensive, case control, and believing that approximately whatever you get also it is what you will have gotten if you have done the course study that is very, very expensive. Even though you say approximately, it is not still the same. So the intelligent people now came with the formula because it is easier for people to do cross-sectional descriptive study, case control study than course study, especially among the academic that nobody sponsor. Because to do any expensive study, you must have sponsor. So you see that many publications have odds ratio. It's only few you see relative risk because that type of study is rare unless somebody organization is funding it. So intelligent people now come with the formula that if you have a study, you calculate the odds ratio. There's a way you can calculate what will relative risk be if you have done cohort study. So that is the corresponding value of that relative risk. If you have done, if you did odds ratio, you did case control or consider the series study and calculated odds ratio, what will have been the corresponding relative? Because the relative risk is actually the one that actually measure the risk, compare the risk among the group, not odds ratio. Because odds ratio is just a proxy relatively. And now going with this formula. So now the last thing we want to discuss is how criteria for judging association. You did your relative risk, it's 5, it's 10, it's 20, whatever value. How do you judge? Is that value? Yes. The thing is causing no. So an intelligent man in UK, I've forgotten the name, but I think I have in my document. He was the one that did this work and came with these 9 criteria for judging association. And these 9 criteria they are arranged according to importance. The most important, followed by the least important is the last one. So temporal sequence number 1. Before you can say a particular, for example, somebody you did it so you say, obesity is a contributor to hypertension. Have you established temporal sequence that obesity is a contributor? I did your analysis. Most of the people that are obese are the ones that have hypertension. In your study, when you establish a temporal sequence. And it's only longitudinal study that can do that. Cross-sectional study can never establish that. Because cross-sectional study, both at the same time, when you are doing the study, you get information about the exposure and outcome at the same time. So you measure somebody's blood pressure. You also measure the BMI at the same time. And you now did the analysis and now say, yes, obesity contributes to blood pressure. You cannot establish, you cannot say that every person you attended to had the obesity before they developed blood pressure, high blood pressure. Because some of them, they were not obese before. They were hypertensive before they became obese. And we are not saying hypertension causes obesity. We are saying obesity causes hypertension. So if somebody was hypertensive before it now became, how can obesity cause the hypertension? So you must be able to establish temporal sequence. If the work you did, the study has not established temporal, that is where the issue of comparing cross-sectional descriptive study with case control. Case control is that better in that, because in case control, if you make someone that is hypertensive, you may ask, you may ask the issue, when was he obese? If the person either is obese or not, was she obese in the past? Be able to, the person may tell you, yes, he was obese in the past before the blood pressure came. Can you see now? You can establish it. For core study, in fact, that one is excellent. You can establish it. So for the longitudinal study now, where you can separate when the disease occur and when the exposure occur, that one, you can do that both in core study and case control study. But you cannot do that in a cross-sectional study, because at the same time, you measure their both attributes. So temporal sequence. So temporal sequence means that the exposures precede outcome. So you must, that's number one thing first. You must be able to establish temporal sequence. The second one is the strength of association. How strong is the effect measured as relative risk or odd ratio? So that odd ratio, if you say odd ratio is 2, it's different from when it is 10. 10 is stronger than 2. It's different from when it is 15. So can you see? You have to look at the effect. If the odd ratio is 1.2, 1.3, you know that it's just 10% higher, 20% higher, 30% higher. When it is 10 now, it's 9 times greater. That's what you mean. It's 9 times greater. When it is 5, it's like 4 times greater. So the issue that is, we are talking of 400% increase. So the strength of association. The consistency of association is number 3. If many study, not only your, many study have been done and they are getting similar results in different locations, in different places, doing the same study, they are getting similar. That's consistency of association. And that's when you can establish that one if you do literature review. When you do systematic review, you will get that in most of these studies, they get consistent results. Then number 4 is biological gradient, dose response relationship. This one has to do with does increased exposure result in more of the outcome? For example, now, if you study maybe varicose vein among women, and the use of OCP, oral contraceptive pill, if the probability of having varicose vein or the probability of having that increases with the dose or the exposure to that OCP, maybe by the virtue of the dosage and for how long the person has taken it. That is a dose response. Or maybe cigarette. Somebody have lung cancer. The prevalence of lung cancer increases the more the person smoke, as per the number of pack per day and the length of smoking. That's dose response. That's what that is actually contributing to it. Mind you, is not number one. Specificity of association, which is 5. Does exposure lead only to outcome? In some situations, the exposure only lead to that outcome. That exposure, that is the only thing it causes. So that is, if you look at this number 5, the exposure, because if that's the only thing it causes, well, doesn't mean that another thing cannot cause that thing. The exposure may be causing, that's the only thing causing. It doesn't mean that it's always the one that is causing it. So, but of course, it's a clue that that particular thing, that's the only thing is known to be causing. Like asbestos exposure cause asbestosis. Now, biological plausibility, number 6. This one just talk about, does the association make sense? You know, someone can just do statistics. Statistics is just an instrument. And you, maybe as a doctor, from your experience, does it even make sense? Because somebody can just, accusation can just happen spuriously. So is you, based on your exposure, based on your level of experience, does it make biological sense? Something is, how does it happen? That's why sometimes the doctor will study the pathogenesis. They want to explain the cause. How does it cause it? It's just like, how does pharmacology, you say, how does the drug work? So if you cannot link it, you can have association statistically, but let the people expert in that area look at it. Does it make sense? They have to study? Does it make biological sense? Even though that one also is not number, is far down, because there are some things that didn't make sense before. Later, people discover that it makes sense. We look at Albert Einstein. When he first of all talked about the law of relativity, he shook the scientific world. The scientists of that time, it doesn't make sense, nonsense. They say it's absolute nonsense. They discovered it. Because it didn't make any sense to the scientists at that time. But later it found to be true. So now, that is why it's not number 1 here. Where we have coherence, number 7. Coherence with the existing knowledge. Is the association consistent with the existing knowledge to what is known before? So if you look at this one also, though it makes sense better if you look at this number 7. Because sometimes, let me give an example. Many times I've been analyzing project and I discover they also talk about when they do anthropometry, when they do what do I call it? Nutritional status of under 5, or yes, under 5. When they were asked for the history, the person was exclusively everything. We discovered that. I've discovered over the time that when it comes to underweight, wasting, all those stuff, is higher among the people that were say they were exclusively breastfed. So sometimes the last time when somebody was presenting, one of our postgraduate students, the external assessor was saying, this one is not consistent with what the WHO has said. When the WHO said, you know what you. The issue is that you know that many a time when these women, they discover that, look, they feel that this is not enough. They are still breastfeeding, but they go and bring formula, all sorts of things, and the child will grow bigger. So at the end of the day, so exclusive breastfeeding is most of the the child, you can say that the child will be healthier, all those stuff. But to say that the person that is not exclusive breastfeeding, we have a low the wasted money. No. In fact, those people that are not exclusive breastfeeding, that they do formula, they do grow bigger. And that's the finding. So now it's not consistent with the existing knowledge. Because the existing knowledge now is that, exclusive breastfed people, they are healthier, they are likely not to be That's what they are saying. It will not be wasted in a lie. So it's not consistent with the existing knowledge. But it doesn't mean that it's not true that the exclusively breastfed people are more likely to be underweight than than the. Of course, we know that obesity also will be commoner among the people that were not breastfed exclusively. So, experimental evidence as randomized control trial be done. This randomized control trial, which is considered the gold standard for you to study the effectiveness of a particular treatment modality. The issue here is, yes, it is, but it's not in all situations you can do experiment, you can do experimental design, because it's not ethical in all situations. In fact, it's on few occasions you can do experiment. For example, now you want to study lung cancer, now say we want to prescribe. There's some people smoke. See, experimental design. You now went to buy St. Maurice or whatever, and that gives them, you recruit them, they have to help you smoke. It's not ethical. Since you've already known that, or there's this injunction that this thing is dangerous to health, you cannot give it to people and that's say you are doing experiment. No. So it's only on few occasions you can do experiment. So that's why. So as experiment, the experimental evidence, if you look at it now, it's last to the least important one there. So because you cannot base our judgment completely on that. And the last one is analogy. Is the association similar to others? If the association you are studying others, is it similar to others? Maybe there are other risk factors also that for that disease. So if you look at it, you see that the most important thing is number one. The least important is the last one. So I think that's the end of the lecture. I don't know if there's any question. Any question? Are we around? I know that 5 people are on board.
We're around. We're around.
We are around, sir.
Yes, no question.
It's well understood.
Okay.
Understood.
Okay, that's fine. Thank you. Thank you for
Thank you,
your
sir.
audience. You're welcome.
Thank you so much, sir.
Welcome.